Welcome to Breaking Math. I'm your host, Autumn Fnaf.
And I'm Noah John-Siracusa.
So today's a little bit of a new session that we told you about on our last episode. We are going for some questions and answers from the audience. And if you want to join in for a future session and have a question for us, you can email us at breakingmathpodcast@gmail.com. Submit a question to our Patreon, or you can join us on our Substack, where we're going to have a little Q&A box for the community, and you might see your question pop up on the first session.
That's pretty cool.
So, Noah, you've been the guy that has explained a lot of AI, and we've been wondering, why is AI bad at math?
Well, I think it's cool because it's a bit of a misnomer. It's not one thing, just like humans are not one thing. That's like saying, why are people bad at math? Terrence Tao, I would say, is pretty darn good at math. Many people, often myself when I'm at a restaurant trying to figure out the tip, are quite bad at math. But there's not one thing as a person, and there's not one thing as an AI. So kind of what happened was, it really depends on how you're training these AI systems, what you're intending them to do. Unsurprisingly, impacts what they're good at. So early on, we were playing with chatbots and large language models that are really just based on predicting words and having conversations. And there's all these funny foibles, like they couldn't count the number of R's in the word strawberry. They look really bad at basic math. And that's because they weren't trying to learn rules and principles and logic. They couldn't learn a system like algebra. You can have an equality and add something to both sides and it still equals. They don't learn that. They just kind of guess and look what's plausible. And it turns out that works great for a conversation where things are all kind of imprecise. That's just how language is. But when you go to math, we really need that precision. But there are systems that are fine-tuned or custom-tailored or really designed to do math. And within the last couple months, these have really been taking off and doing amazing things. They can now solve all these Math Olympiad problems, Putnam problems. There's even been some evidence I've seen on some really cool discussion on Twitter /X and probably other platforms of them really doing, like, I don't quite want to say novel research, but helping mathematicians do some novel research. One found this like obscure reference in a German journal from the 1970s that had like the key lemma that helped them solve a problem. So AI now is very good at math, but that doesn't mean if you're using a chatbot, it'll be good at math. So really think of it as tools. It's sort of like saying, why are hammers so bad at putting screws in, and why are screwdrivers so bad at working with nails? You need the right tool for the right job. So that's how I like to think about AI.
That's always fascinated me because I have never thought about it that way. You give it a prompt, it does some random walk behind the
Yeah.
scenes that we don't see, and it just makes sense of
Sometimes
whatever
it does,
we're doing.
sometimes it doesn't. But
See?
that's again thinking of it's kind of making AI monolithic. And I think it really helps to think AI is a set of tools and you have to choose the right tool. And some are sharper and duller than others at different things. So it really varies. But speaking of tools, let me turn to some mathematical ones. So this one's a great question that I think is perfect for you. What's the difference between calculus and algebra? And I'll say, I'm a math teacher and I teach both of these things. I've never even thought to ask that question. So let me just thank the user who said that, or the listener. I think that's an awesome question. I never would have thought of it, and I'm very eager to hear your answer.
So, difference between calculus and algebra is actually really, really simple. Algebra is about describing the relationships between symbols. So, it helps you express patterns and compare quantities and also solve for unknowns. So, when you're working in algebra, you essentially treat the variables as placeholders and ask questions such as, what is the value that X will make? How does it depend on Y? So, these relationships are stable. And once you write them down, it doesn't really change unless you change that equation. However, when we're moving to calculus, this is actually something that's building on algebra, and it's going to focus on what happens between the relationships as they vary continuously. So when you're looking at the changes, you're looking at something at any given point in time. And calculus will zoom in on this infinitesimally small increment, and it's going to let you measure how fast something is changing in that exact moment. So that's why calculus and algebra are taught separately, essentially. And calculus is essential for understanding motion, growth, optimization, and some of the natural phenomenon that we don't see in these finite steps. So algebra gives you the rules of the system, and then calculus essentially shows you how that system behaves over time. And you can think about that as either time or space, and you can keep going up in multiple dimensions because it isn't just two variables. It could be four or eight.
That is amazing. And I can't help adding something that's not directly in this question, but it's just amazing thing. So I used to teach at Swarthmore College, a liberal arts college. I know, Autumn, you've been at liberal arts college as well. One fun thing is you get a kind of integrated education where literature comes in and art and all these things. And this has certainly come up on the podcast. So here's a little kernel that I read about, I think when I was teaching something at Swarthmore that just always stayed with me because it's just kind of so mind blowing. So this reminds me of this amazing episode in math history in, I think it was like the 1890s, where people were really interested in continuous functions. And Autumn, you mentioned that calculus is about these functions that are changing continuously. Kind of what happens is there's this thing called an analytic function. If you know what it is, great. If not, don't worry. But it's the main functions people study in calculus. And it turns out analytic functions are very predictable. Like if you know how they behave in a tiny neighborhood, it's sort of like Taylor series. If you've heard about this, you can understand how they behave all over the place. And what these Russian thinkers, mathematicians, and philosophers, whatever you want to call them, were saying was, wait a minute, an analytic function is basically saying that there's no free will, that everything is completely predetermined. Like once you have that function here, everything is mapped out. But discontinuous functions, that's where free will is. And they built this whole idea that like free will in the human brain is all, and kind of going against some ideas in religion, are all about discontinuous functions. One of them even put together an argument against the Tsarist regime. So, like early days leading up to the Soviet Revolution, that was all based on discontinuous functions. So it's just amazing to me. Like when we study calculus, it's like, oh, you can compute the volume of some solid or the area under a curve. It just feels kind of like engineering. So it's amazing to think there was also calculus that was like moral and political and just like deeply meaningful to some people.
But did you know that there was actually somebody before that
Okay.
in about 1700s that was the one who put that together chronologically?
I actually don't know the story.
Okay, so there was a woman,
Hmm.
Maria Gitana Agnieszki, born in Milan in about 1718, and she was part of a very wealthy family. Her father considered her an intellectual centerpiece, despite the fact that she was very, very introverted. All she wanted to do was read and write and study. And by about the age of 17, she ended up speaking 7 languages. That isn't including mathematics, if you want to get technical. So she probably spoke 8. She was such an introvert and so deeply religious that she longed for periods of study. And her public brilliance at one point was not an ambition, it was an obligation. What she did with her brilliance was she studied mathematics. And in 1748, she was probably about 30 at the time, she ended up publishing Institutioni Analyticae, which was the first comprehensive calculus textbook ever written.
And I hear that same word analytic that we were just talking about.
Yes, she ended up unifying all of the algebra, geometry, and diffie-hughes and integral calculus into this one coherent framework. And it was translated all throughout Europe, praised by Euler. And it was probably one of the best calculus textbooks of the century. From there, she was given this honorary professor position, and that was handed to her by the Pope. However, she said no, which was something very, very untraditional at that time. When you are handed something as a woman studying mathematics or studying science and that being prestigious, that was something that just didn't happen every single day. However, during that time, there were some very interesting translation errors that had nothing to do with mathematics. So when she was written about, she was actually deemed as the Witch of Agneski. And it was a name not exactly given to her, but it was actually a spelling mistake for a very tiny meaning in the name. And it was called The Witch That Turns. Very sloppy English. But what ended up happening was that she came out of the public eye And even though her work wasn't technically erased, she opted out. And what she ended up doing was essentially becoming a hospice nurse
Wow.
the rest of her life. And she's like, I'm done. I'm done with math. And her legacy was more kindness than mathematics.
Reds, I want to pick up on there. I know this is a Q&A, but we're getting to know each other, Autumn, right? We're allowed to discuss.
Yep.
So one is, I can't resist pointing out, in our last episode, Salem, Massachusetts came up and this photo of you. And I feel like you've somehow found a way to bring witches into every episode we've done together.
Not yet. I promise this won't happen every time.
Okay, well, so far you're 2 for 2, so I'm impressed and scared in equal proportions. There's some funny examples. So my wife is an opera scholar. Probably a lot of people have heard of Rossini. He did like the William Tell overture. Apparently he retired from opera composing pretty early. I forget what age, maybe in his 40s, and then became a chef. And he just like cooked all these dishes and just enjoyed life, eating and cooking. He was done writing opera. He made his career. So sometimes people do this. They pivot and transition to new careers.
I just find that to be interesting, especially when someone gets tired of what they're doing in
When they're like
academia
the
or
kick-ass, the rock star at what they're doing. They
yeah,
reach the pinnacle and then they're like, all right, on to something else. It's
of
amazing.
course.
The
So
other
it's
thing,
like
it's kind of obvious in what you're saying, but I think it's worth emphasizing is we are so hungry for important examples of women in math and science history, but it's frustrating to hear these amazing examples and think like, why did I not know about her until just now sitting here talking with you? Why is she not more well known? Why is her story not more well known? So I don't know. It's kind of exciting to hear of these things, and it's frustrating that I'm today years old when I finally find out about this.
I mean, I think there was a something very important that I've found when going through science research and just even economics research that I learned. If you look on Victoria Bateman's Instagram, she has a bookshelf on there. And it shows all of the scientific discoveries in economics written by men and books that highlight men. And I think she had a quarter of a shelf written by women. So you can see how many women have been erased throughout history. Popes were the people who gave power for professor positions. So this
That is
plays
amazing.
in a patriarchal society, even though I will say a lot of women ended up being the ones who ran the society quietly. But it depends on what sort of lens you look at. If this is through a Western European lens, or if you're going to shift over time and you're going to look at the Middle East and trade agreements, who was running the countries, there was a lot of women. And we don't always highlight that in our textbooks.
That reminds me a little bit of the Hidden Figures story, where there are women doing important work, but it's often not considered important until men kind of take over and do it. And then everyone's like, oh yeah, computers, that's the really important, serious, stuff. Women are doing other things. But when women were the ones working on computers, it was considered more secretarial. So it's like the prestige is it's so focused on how society is placing it rather than it's not an impartial thing. It's not like, oh, math is prestigious and other things are not. It depends who's doing the math.
Precisely. Speaking of math, we have a question here that asks, is infinity real?
All right, so that's a great one. I'm glad you tossed my way because that connects to math history. So it's a perfect one to talk about. I would say anything can be real in math. That's one of the beauties of math, as long as it's kind of internally consistent and it doesn't contradict other parts of math. So what I mean by that is in physics or many other fields, you have to go and look for things in the universe and measure them and see if they're there. Maybe you have a hypothesis that there are black holes and no one believes you. And then you get measurements like, oh, see, I was right, they're black holes. But math lives in our minds and we can invent whatever we want. We can talk about something called infinity. We can make it real, relative to math, within math, as long as we can find a way to define it that doesn't mess other mathematics up. If we just define, like you're not allowed to do divide by zero on a calculator. If I define infinity, let's say like anything divided by zero to equal infinity, that's actually a problem because what if I did negative that number divided by infinity? Then I really should get negative infinity. So then you have to figure out which one are we talking about. So it turns out there are bad ways to define infinity, but there's also good ways. There's geometric ones. There's something called the projective plane, where two lines that are parallel, if you think of like the rails on a railroad or the ends of a road, as they go up to the horizon, they stay parallel, but they look like they get closer and closer. And at infinity, they seem to meet at a point. So you can define a geometry, and it's called projective geometry, where parallel lines do meet at a single point. and you call that the point at infinity, and that brings infinity into geometry. You can bring it into arithmetic, into all kinds of things. But the mathematician that really kind of owned infinity the most is this guy named Cantor in around the 1890s, so similar time frame as I was talking about as the other Russian discontinuity stuff. He found this, he basically invented set theory, which now when we study mathematics, I would say we don't even think about, you just take it for granted. But someone had to come up with set theory, what sets are and how they operate. And he came up with it. And let me just say this, for a while, people felt that infinity was a limit of a process. Like you could talk about, let's say, to make it really concrete, you could talk about the natural numbers, 1, 2, 3, 4, 5, dot, dot, dot. And everyone knew they kept going without limit. You could keep counting higher and higher numbers. There is no the biggest number. But for a while, mathematicians didn't think you could consider all natural numbers simultaneously. And Cantor said, we can create a set. We'll call it the set of natural numbers, and you can denote it with a fancy n. And this set has certain properties. For instance, it's the size of infinity. So he kind of allowed us to work with infinity. And in doing so, he actually realized there are many infinities. There's actually infinitely many infinities. So that gets into a whole thing called set theory, and Cantor is the biggest name if you want to look up him on Wikipedia. But the punchline is, yeah, in math, infinity is real, but it's not like a kind of automatic God-given real thing. It's something we have to define. And I would say the geometric definition is very different than the Cantor one, but they both work. They achieve the goal that we need.
Amazing.
It's cool stuff. I love, these are all topics that I've learned about through teaching, and I just love, like, I don't know, I learn a tiny bit to teach my students and a lot more because I'm just like, this is so cool. I want to know more. And Wikipedia is a great source. You can get a lot of information.
Wikipedia can be edited and it's not always fact
Okay.
checked.
It's not always great for like pure factual accuracy, but it's like a chatbot. It can push you in an interesting direction. You may not always get 100%, fidelity to the truth, but you'll find
Yes,
interesting things there.
exactly.
All right, I'm going to scroll through. Here's one that's, I think, more in your wheelhouse than mine. Where does pi, I presume they mean the number, not the food. Where does pi come from?
You talked about measures of infinity, but pi is actually where you compare the circle's circumference to its diameter. So ancient civilizations didn't exactly have it as pi, but they did notice the Babylonians in approximately 1900 BCE. Pi was about 3.12. Egyptians looked at pi at about 1650 BCE as 3.16. So we've got some close approximations here. And then Archimedes, in about 250 BCE, trapped pi between polygons inside and outside of a circle. Archimedes' idea was a bit more genius than we would expect. You can approximate a circle with a many-sided polygon. So he was starting to use calculus. As the number of the sides increase, the polygon becomes much more circle-like. Then, as the perimeter approaches the true circumference, you end up getting about 3.14. And then he just took that as far as possible. Now, this is an early glimpse of calculus, and it shows up essentially everywhere. That's in waves, that's in probabilities and statistics. And something now that we're looking into is quantum physics, heat flow, and signal processing. Why does this matter when you're looking at pi? Because you have everything from symmetry, rotation, and you need smooth curvature for so many different equations in our systems. And pi essentially doesn't tell us about just circles. It's telling us how space is behaving when things are real and things turn and when they repeat.
All right, now let me give a little riddle to our listeners.
Go for it.
This is something that just came up one time when I was teaching, and I just honestly thought, what? How is this possible?
Okay.
So imagine I want to compute the distance from point A to point B, and there's two options. I could take what's called the Manhattan metric or taxicab metric, where I just go like east-west and then north-south. And let's make it simple. Let's say it's one block east and then one block north. So I've gone a total distance 2. The other option, of course, is I could take the hypotenuse, the straight line, the distance as the crow flies, and that's square root of 2. So, 1.4 roughly instead of 2. So obviously it's shorter. But here's what I'm going to say. What if I approximate, very similar to what you said with Archimedes and the circle and the polygons, what if I approximate this Manhattan path where now I'm allowed to take these like half blocks? Well, I can go half a block, half a block, half a block, half a block. But if you add up all those north, south, east, west distances, it's still 2.
Still the same.
Now I do quarters, and I have this little jagged path, and I add up all the east-west distance and all the north-south. I've still traveled 2. Now divide it, divide it, divide it. I can keep taking finer and finer until eventually I have this tiny little jagged path that's kind of approximating the hypotenuse, and its length 2. And I can take the infinite limit as this gets finer and finer and finer, and at every step of that limit, the distance is 2, and yet somehow in the infinite limit, it magically pops to zero point 0.4. How in the world can a limit of a constant sequence of all 2's suddenly pop into this much lower number? So it's just to say the process he described with computing pi, it's actually, I would say, more deep and profound than we might realize. It might seem obvious, like, oh, if you keep taking little straight line approximations, eventually you get round. But here's an example where I have straight line approximations of a diagonal line and weird stuff happens. So I don't want to give away the answer, but I'll let our listeners think about that one a bit.
And if you're listening at this point, tell us why in the comments.
Well, yeah, that's right. You can email, you can do comments, all kinds of engagement.
If
We
we
love it
have
all.
that on most podcast platforms, you can actually have somebody put that in the comments.
Oh, wow.
So
That's awesome.
if you are listening, put that in the comments.
Love it.
So thinking about all of these different formulas, I was shopping at Target the other day. And I found this, I went on the app, I was going to go into the store, and I just made a little click through my cart. It was for a book, and then it was a t-shirt, and then I just wanted to go get some Tostitos chips.
Fair.
And when I was in the store, I noticed that the price was a lot cheaper than it was on the app. Now, we got a question asking us about dynamic pricing. What is it, and why are stores doing it?
I am so glad. I was so glad to see this in our listener questions, and so glad that you're tossing it my way because for whatever reason, people have been asking me a lot about this lately. Some to the extent where I didn't consider it like one of my topics. So many like people in congressional offices, attorney general office, journalists, someone at who writes for a magazine about airlines. So many people have been asking me about this that I decided I got to just embrace it and say this is one of my topics now. So, dynamic pricing. All right, here's the story. Dynamic pricing, we're mathematicians, mathematical audience. Dynamic really means sort of changing, like changing with time, a dynamical system, a dynamical price. So when you talk about dynamic pricing, my interpretation is they really just mean prices that change, perhaps quite quickly. So the kind of canonical example of this is with airlines. I go to, let's say I'm going to buy a plane ticket to California. I look up the price, $400. Then the next day I check the price, and it could be half that or it could be twice that. So it's fluctuating very rapidly, much more than if I go to the grocery store to buy milk. It's pretty constant. Maybe it goes up or down a little bit, or there's some weather or shortage or supply chain issue. But airlines, their prices are just all over the map, up and down. So they're very dynamic. And it turns out a lot of them use these complicated dynamic pricing models that do incorporate not just supply and demand, but weather, events that are happening. And there's various ways people feel about that. Some is like, that's the market. They can do what they want. Some is this is kind of taking advantage of us because it's very frustrating when I go and the price changes so much and I don't know why. And I don't know when I'll find that good price. But now the reason why this is coming up a lot in the news lately is it turns out we've spent 20 years, not you and me, Autumn specifically, but humanity has spent 20 years building this whole technological infrastructure around what some people call surveillance capitalism to basically collect as much private personal data around people as possible and to use that data to target everyone with ads. So we all know when you go online on social media or on the web, you see ads and often they're targeted. Maybe I've seen an ad for a basketball and I was just outside playing basketball or I was watching a basketball game, but it just seems to like follow my interest in what I'm doing. Of course, that's because somehow they've collected my data. Maybe they bought it. Maybe they tracked it on the web. Who knows? But they have my data and they use that. And now there seems to be a lot of interest in companies using that same infrastructure, that same data pool to not just target us with ads, but to individualize our prices so that maybe I'm watching a lot of TV that suggests I have a higher budget than you. So when I go on Amazon or if I go on Instacart or Uber, maybe I'll see higher prices than you. So that data can help them figure out how much I'm going to pay. So this is now leaving dynamic pricing and moving into this, I would say, scarier thing called personalized pricing, or some people even call it surveillance pricing. They're really surveilling you. And I'll just say this, it's not widespread yet, but concern over it is very quickly raising and becoming widespread because if it happens on a widespread, if there's a lot of this surveillance pricing, it's very uncomfortable. It's very scary because we as the users don't know what's going into our prices. And it's just weird to think that like me and my spouse may pay different prices on Amazon or on Uber. And actually, let me give you one concrete example that has not been definitively proven because nobody knows on the outside of these companies what they're doing, how their algorithms work. That's part of the problem. But this is something that actually the FTC, the Federal Trade Commission, so a big government agency in the US, has cited as like an example of why we need to get ahead of this technology and try to stop it before it gets too late. Which is, someone did a study and it looks to be the case that ride shares, so I don't know if this was Lyft or Uber or both or other ones, but let me just say ride shares to be safe, that rideshare apps, one of the factors that seems to go into their pricing algorithm is your phone's battery life. Specifically, when it's really low, they increase your prices. And so the
Interesting.
idea is like, let's say, I don't know, you're in New York City, you're standing at the street corner, you're really like desperate to get home, you're planning on taking the Lyft home, and your battery's down to 5%. You're going to be willing to pay a lot higher price because like your phone's running out. You don't want to be stuck on the corner. So it turns out this is a general phenomenon. When people are desperate when their phone is low, they do pay higher prices. And this does seem to be. So some people outside these companies did experiments and they found that when the phone battery life is lower, the prices are higher. We don't know for sure if this is happening. It just seems to be. We don't know how widespread, how many companies do this, where this is showing up. But it's just kind of making us think this could be a big thing and it feels very creepy. So that's it's dynamical pricing and personalized pricing, and that's something that a lot of people are worried about right now, and I think rightly so.
This makes you really think about all the different algorithms that are influencing our world every single day. So, as I like to tell folks, if you're interested in learning more or asking us more questions about the systems that influence our lives and some of the mathematical questions, feel free to email us at breakingmathpodcast@gmail.com, subscribe to our Substack, and also our Patreon. And until next time, stay curious and stay informed of the world around you.